Good morning, everyone, and welcome to our second lecture on the topic of congestion control. If you remember, this is a topic that we started last time, where the last time we talked about at length about what is the problem of congestion control, why is it important that we address it, and then we also talked about kind of the broader space for this congestion control solutions, as well as identified kind of one slice through the space of design options that we said would be how TCP does congestion control. And again, just recall that slice that we identified was based on three characteristics. The first was that we were going to look at solutions that were host-based congestion control. This means that the sender in particular is on its own figuring out what rate it should send traffic at without any assistance from routers along the path. The second aspect we said was that the manner in which we implement congestion control is going to be to have the source dynamically and constantly discover and adapt the rate at which it's sending traffic into the network. And the third dimension was we said that in order to know whether the network is congested or not, the sender was going to be looking at packet loss as an indicator of congestion. And we talked about the pros and cons of loss as well as other options like delay. But we said going forward, we're going to be kind of honing in on loss as an indicator of congestion. And so the plan for today is to, kind of look at how the same approach that we've discussed last time, but how TCP implements that approach. So there's no new algorithms or, design options really that we consider. It's really a deep dive into one particular way of implementing that design option that we identified the last time around. And so the plan for the lecture is I'm going to start by actually reviewing how TCP's window-based operation proceeds and how it does reliability in this kind of sliding window paradigm. And part of why I'm doing that is because when we talked about TCP reliability, we didn't really step through in detail how TCP reliability works. So we're going to do that today. Even though the basic building blocks we stepped through, we didn't really step through the TCP design for reliability. So we'll start there, review how the window-based operation works, and then we'll talk about how that operation or that design is extended to do congestion control. And as you'll see, the way in which TCP does congestion control is very intertwined with how it does reliability. For better or for worse, that is how TCP is implemented. And so it's very hard to tease apart how TCP does congestion control without also actually talking about how we do reliability. So with that, just a quick review. Again, as we've said many times, the sender maintains a window of packets in flight. These are packets that it has transmitted but hasn't yet received an acknowledgement for. And we said this window size is based or picked to balance three goals. So this is the actual value of the window size. And those three goals were to fill the pipe, to avoid overloading the receiver, which we call flow control, and to avoid overloading links in the network, which is today's topic of congestion control. We first said that the last goal subsumes the first one, and so really we just have to worry about flow control and congestion control. In terms of implementation, we said that flow control is achieved by having the sender maintain what we called was the advertised window. I'm now telling you that advertised window is also sometimes called receiver window, and the typical parameter that we use to denote this value of the window that the sender learns is rwind, which stands for receiver window. So advertised window, receiver window, they mean exactly the same thing. The parameter rwind refers to either of those. And then to implement congestion control, we have an additional parameter, which is this congestion window or cwind. Okay. I'm going to repeat this one more time because all these windows can be confusing. Congestion window or cwind is how many bytes the sender can put into the network without fear of overloading the links in the network. This is computed, or the value for cwind is computed by the sender using a congestion control algorithm. And that's what we're going to talk about in the rest of this lecture. The flow control window or rwind is how many bytes the sender can receive without overflowing the receiver's buffers. And this was implemented very simply by having the receiver tell the sender what its advertised window value should be, and it does so by communicating that value through the ACKs. And then finally, at the sender side, the true window size that it uses is the minimum of cwind and rwind. Right? That's intuitive, I hope. For this lecture, we're going to assume that flow control is not the bottleneck, that it's instead sea wind. So we're going to assume our wind is much greater than sea wind. And so everything we're talking about here, the sender's window size is going to be determined by sea wind. In practice, this is also fairly true, which is typically the sender's rate is determined by its congestion window, but not always. And so we have to remember to keep both of those values in mind. Another note is recall that TCP operates on byte streams. So we said all of the accounting that TCP does in terms of sequence numbers, acknowledgements, and so on are in terms of an offset in the byte stream that the sender is sending the receiver. In real implementations, sea wind will be maintained in bytes. It's the number of bytes that the sender can put into the network. For our convenience, this lecture we're going to talk about sea wind in terms of units of MSS. So MSS, again, a reminder, was the maximum segment size. This was the maximum number of bytes of data that one TCP packet could carry in its payload. So roughly, intuitively, you can think of, units of MSS as being roughly the same as packets in terms of the discussion we're going to have in this class. But remember that real implementations and also, problems on the exams and all, we would be asking you to do sea wind in terms of bytes. So I'd like to start with a quick review of TCP reliability, and in particular this notion of a sliding window and how that protocol works. And so going back a few lectures, we said that a sender maintains a sliding window of W contiguous bytes. And so in this figure here, if my window at the sender starts at a byte offset of I and my window size is W, then this range of bytes from I to I plus W, that constitutes the sender's current window. What this means is that any bytes less or lower than the left-hand side of this window, less than I, the sender has already sent them, the receiver has ACKed them, and the sender has received the ACKs. So these are bytes that the sender understands have been reliably transferred. We're done with these bytes. The sender is free to release the buffer space associated with those bytes. On the other hand, the bytes above I plus W or over the right-hand side of the window, these are bytes that the sender has never yet transmitted, and it's not allowed to transmit it either, given the rules of the sliding window protocol. And so the sender is only allowed to transmit this range of bytes that are between I to I plus W. Whether they've been ACKed or not, we don't know at this point. In addition, the sender, we said, associates a single timer that's associated with the left-hand side of the window. So if you remember, we said that TCP, you don't have a timer per packet or a timer per byte offset. Instead, we just have one timer associated with the left-hand side. And when that timer fires or you have a timeout, then the sender is going to retransmit the bytes, the set of bytes starting at the offset of I. And so that was the basic sender side behavior. On the receiver side, we said that TCP reliability implements cumulative acknowledgements. So it's going to acknowledge the next expected byte. And we said that the sender counts the number of duplicate ACKs it has received. We also said that when the sender has received a certain number of duplicate ACKs, which we said was 3, it was going to retransmit again from the left-hand side or the first set of bytes that are missing at the receiver. I don't think we introduced this term before. This process of retransmitting when you receive 3 ACKs, that is called fast retransmit. Okay, so this mechanism of I'm going to count the number of duplicate ACKs. If I receive 3 ACKs, I'm going to treat it as a loss and retransmit. We call that fast retransmit. If the sender receives an acknowledgement for new data, so let's say that the receiver is saying that my next expected byte is J, for some J greater than I, then what the sender is going to do is it's going to slide the window right. So now the left-hand side of the window starts at J. J is the first byte that the sender can send, and it can send up to J plus W. Okay? And this is where the kind of sliding window analogy comes from. Every time you get a new ACK, you slide your window right. And it's, again, remember, always W contiguous bytes that the sender can send. So that was a quick review of how TCP reliability works and this notion of a sliding window protocol. Moving forward, what we're going to be looking at is how we extend TCP and that sliding window design in order to incorporate congestion control. And so step 1, as we've mentioned, is we add a parameter that we call the congestion window or sea wind. And beyond that, the general idea is going to be that we adapt sea wind based on the current congestion level. And how should we adapt sea wind? if you recall from last lecture, we were talking about the sender adapting its transmission rate. Right? So we said when you additively increase, then you increase your rate. When you multiplicatively decrease, you decrease your rate. Okay. And so what is that rate and how does TCP do it? In TCP, the sender's rate is simply the congestion window divided by the round trip time. Right. This should, I hope, make sense. And again, this is ignoring the receiver window. What is the rate after all? The rate is just how many bits you can send or how many bits you're sending per unit time. Right? 10 megabits per second, 100 megabits per second, whatever. It's bits per unit time. In TCP, the sender, if you think about it, is sending a C-wind worth of bytes, and it's sending C-wind worth of bytes on the time scale of a round trip time. Right? That's how many bytes I can, as a sender, I can put into the network. And then in a round trip time, I will start receiving acknowledgements back that will allow me to send more bytes. But so the sender's rate in TCP language or in TCP parameters is simply C-wind, that's in terms of number of bytes, divided by the round trip time, which is in units of time. And so that's giving us kind of the bits per second or the sender's rate. Okay. And so if the sender's rate is C-wind divided by the round trip time, then the way in which TCP is going to adjust its rate is simply by adjusting this parameter of C-wind every round trip time. And when it adapts C-wind every round trip time, effectively the sender is adapting its rate exactly like we talked about in the last lecture. Okay, so again, recalling, last time we said that the congestion control had three basic components to its design. There was how you detect congestion, which we were going to say was going to be loss-based. There's how you discover your initial rate, for which we had slow start. Remember this idea of you start small and then you exponentially increase. And lastly, how you adapt to congestion, your rate to congestion, these increase-decrease rules. And we talked last time at length about why AIMD, or additive increase, multiplicative decrease, is the correct approach. So what follows in all of our slides is really how TCP implements the above solutions. And the theme you're going to see in how TCP does this is that all updates to C-wind, because remember we said adapting your rate means updating C-wind, all updates to C-wind are going to be driven by receiving acknowledgements. Okay, so if you think of this in terms of kind of some event programming, your events here is the arrival of acknowledgements. And of course, timeouts as being, the absence of acknowledgements. But other than timeouts, all other updates are going to be based on receiving an acknowledgement. We call this ACK clocking, and this idea of ACK clocking and that TCP exhibits ACK clocking behavior is something you'll hear quite commonly, when you talk to people who do networking. And what do we mean by ACK clocking? I just want to take a couple slides to elaborate on that. The idea here is that when you receive a new acknowledgement, we slide our window forward. And the process of sliding the window allows us to send some new data into the network. And so we end up with this behavior where when I get a new acknowledgement, I'm allowed to send new data, so I put new data in. And so in some sense, you can think of it as the transmission of data by the sender is clocked by the arrival of acknowledgements. Okay. And doing so has some nice properties that I'm going to get to that with an example in a minute. But in a nutshell, the benefit of doing ACK clocking is that the sender ends up kind of self-pacing, or it paces its transmissions at exactly the rate of available bandwidth. So whatever bandwidth is available in the network, the sender transmits at that rate, but it's also transmitting at that rate in a very paced manner or in a non-bursty manner. So let's look at a figure. I think it's easier to understand when you kind of see it visually and in action. So let's take here in this example a very simple scenario in which I have a source and a destination. And they have three links along the path between the two, and the bottleneck link is 1 gigabit per second, which is 10x lower than the other two links. And for now, for this example, just to demo ACK clocking, we don't even have to worry about competing flows or congestion along the path. Let's just say the source has the entire path to itself going to the destination. And let's look at this in what our old pipe view of the network, where the width of the pipe denotes the capacity of that link. And so here we have the skinny pipe corresponds to the 1 gigabit per second bandwidth. And I'm also splitting the forward direction, each direction of that path. So the forward direction is on top, and then acknowledgements travel in the reverse direction on the bottom. And now let's say that the source had a burst of packets to send. And so it sends a burst of packets. It's on this high bandwidth link. So those packets are traveling back to back in a burst. They travel through that link until they arrive at the bottleneck. And now they're arriving way too fast for that bottleneck. So that burst of packets is going to be queued at that bottleneck link. And then the bottleneck link is going to service those packets or drain the queue at that much lower rate of that bottleneck link. And so what we see is that those packets that were queued are now being transmitted over the bottleneck link. And as they travel the bottleneck, they're kind of being spread out, simply because the transmission time is lower on that bottleneck link. And so it takes, in our view of this pipe capacity view, it takes up more time and more space on the bottleneck link. And so what happens when those packets get onto the next link is that you again have, it's a high bandwidth link, and so the packets are looking skinny again, but they maintain the space between them, which is the space that was set by the bottleneck link. So the gap now between these packets corresponds to the gap that was introduced by the bottleneck link. Again, this should make sense. We effectively have a 1 gigabit per second link feeding into a 10 gigabit per second link. So you're going to have these idle times between packets. So these packets now arrive at the destination, and what is the destination going to do? It's going to pick up each of these packets and it's going to send an acknowledgement. So when a packet arrives, pick it up, send out an acknowledgement. And so when we look at the acknowledgements as they're traveling back, what we see is that they maintain that spread between them, or the gap between these acknowledgements is kind of determined by that bottleneck link on the forward direction when data packets are going from the source to the destination. And that gap is going to be maintained, let's say, on the return path. And so here in this figure, the only reason that the ACKs are not occupying the full bottleneck link is simply because acknowledgements have fewer bytes in them than the data packet. But the important part here is to notice that the acknowledgements in the gap between acknowledgements, or the spacing between acknowledgements, when it arrives back at the source, is reflective of the bottleneck capacity on the forward path. And so in ACK clocking behavior, what happens is, now what is the source doing? It receives an acknowledgement and it puts in a new data packet on the network. And so now after one round trip time, if you look at the rate at which, or the pattern of the sender putting in new data packets into the network, we see that these new packets are kind of clocked, or they're maintaining the spread that was determined by the bottleneck link. So the source is no longer sending these bursts of packets. Instead, it's sending them out nicely paced. And so in steady state, what we would expect to see is something that looks, visually, none of this is to scale, obviously, but visually what we would see is that the sender is fully occupying the available bandwidth as determined by that bottleneck link, but it's sending out these packets paced in such a way that we require no queuing at that bottleneck link. So the sender is sending at an ideal rate, but we're not incurring any queuing. And so the reason people like this is now, it kind of gets rid of some of the burstiness. And remember that bursty traffic is what sometimes causes these transient queuing, and sometimes you end up losing a packet when multiple bursts arrive at the same time. That's much less likely to happen if you have this kind of self-pacing or these nicely spread out packets arriving. Okay, so a bit of a digression, but that is, I wanted you to have a mental picture of what ACK clocking is and why it's useful. Okay, so that was ACK clocking, and as you'll see, all of TCP's implementation is kind of geared around this notion of clocking out data packets by using the rate at which acknowledgements are coming in. And going back to something I said in the last lecture where I talked about Van Jacobson and Carroll's paper on congestion control and how they had in their head this model of the internet or congestion as a feedback control system, and this principle that it should, or this notion that any congestion control solution should maintain this kind of conservation principle, where the notion was that in steady state, when you're going at the right rate, the sender should maintain conservation in the sense that it pulls out one packet from the network, it should add another, only then can it add another packet into the network. So we're conserving the number of packets currently in the network. And ACK clocking is the very elegant way by which they achieve that kind of conservation. Right? I pick up an ACK, I put a new data packet in. And as long as I'm being driven by the rate at which I'm receiving ACKs, then I'm very naturally letting the network tell me at what rate I can put packets back in. Okay, enough with ACK clocking. Going back to our question. So as we said, we had three components to the design, right? Detecting loss, discovering an initial rate, and adapting that rate. So how TCP rather detects loss, we've already covered this. The two ways: either you can have three duplicate ACKs. This typically indicates an isolated loss. Or the second mechanism was that we would have a timeout, which typically indicates a fairly severe network congestion where you've lost several packets in the network. The second design component was this question of how you discover your initial rate. And we said we were going to do this with slow start. And again, the slow start basic idea was you start at a slow rate and then you increase your rate exponentially until you experience loss. So in TCP, how TCP implements slow start is it's going to start with a very small C-wind of 1 MSS worth of data. So this means that the starting rate for TCP, a sender, is MSS over round trip time. So it's really sending one packet every round trip time. This is a very low rate. And then TCP is going to double its congestion window, the C-wind parameter, every round trip time until the first loss. How is TCP actually going to implement this? Going back to our ACK clocking notion, is that every time it receives an acknowledgement, it's going to add 1 MSS to the C-wind. Okay. Why does this end up doubling C-wind over the course of a round trip time? If you think about it, it's because every time, we were saying before that every time you receive an acknowledgement, you've taken one packet out of the network, and so you can put one new packet into the network. That's what we were doing when we wanted to maintain the window size, not change the window size. If instead now I say every time I pull out an acknowledgement, I can send 2 packets into the network, then I'm effectively doubling the number of packets I'm putting into the network every round trip time. And so I'm doubling my C-wind. Let's see that in action. Okay, so the goal again is to double your C-wind every round trip time. And we're saying that the way you implement this is you add +1 to your C-wind every time you receive an acknowledgement. Okay, so let's say the source started with a C-wind of 1 and it sent 1 packet. When it receives an acknowledgement, it increases C-wind by 1, so it's now 2. So it gets to send 2 packets because there were no other packets in flight. When you receive the acknowledgement for the second packet, the C-wind is now 3. And so the source is allowed to send 2 additional packets. Why 2? Because you're allowed to have 3 outstanding packets. You just received one of the previous 2, so you only had 1 outstanding packet left, and so you can add 2 new packets into the network. So the source will then send those 2 packets. When the acknowledgement for D3 comes in, it's going to increase C-wind to 4. It's going to see that it only has 2 packets already in flight, so it's allowed to send +2 packets. And so now you have kind of these 4 packets that are all currently in flight. And it'll go on and so forth. Right? It'll add 1 to its C-wind every time. And so if you look at this, you see that, in our first round trip time, your C-wind was 1. In the second round trip time, it was 2. In the third, it was 4. Next one will be 8, and so on. But notice that it isn't, the way this is implemented, we don't have these abrupt jumps or doubling in C-wind, where in one round trip time, let's say my C-wind was 8, and then in the next round trip time, it was 16, and I suddenly dumped 8 packets into the network. That's not what TCP is doing. It is doubling its round trip time over the course of a round trip time, but it's sending out those additional packets spaced out as the ACKs come in. And so there isn't this overly bursty behavior. Again, ACK clocking in action. Next is how TCP implements slow start. So just to continue, so what we said so far is that we're doubling the C-wind every round trip time until you experience loss. But remember, we said that the goal of slow start is to discover, a good initial rate, right? And so far we've just said, we're doubling our rate every round trip time. Where is that good initial rate? That good initial rate is remembered or maintained by a new parameter that I'm introducing now, which we call the slow start threshold parameter. It's denoted as SS thresh. And this is the parameter that's going to remember what we call a good rate, which is the last safe rate that the sender had experienced. Okay, so the way SS thresh is set is that, remember, we were doubling our C wind until we experienced packet loss. When we experience packet loss, we say that we set SS thresh to be half of the current congestion window. What's the rationale behind this? This should make complete sense, but here's the reasoning. Let's say I was increasing my C wind and it was at 4 and I had no loss. So over the next round trip time, I increased it to 8 and that's still no loss. So next round trip time, I increased it to 16. Still no loss. Yet another round trip time, I increased it to 32, let's say. And now I experienced a loss. So what does that tell me as a sender? It tells me that 32 is not a good rate, right? Because I'm experiencing loss, so I've congested the network. But I also know that at 16, I was fine. At 16, I had not experienced any congestion. I didn't have any packet loss. So 16 is actually a good rate. It's a known safe rate at which the sender can send. And so SS thresh is going to remember C1 by 2, which would be 32 by 2. It's going to remember that rate of 16 as being a good rate. And we'll see when this plays out. But, just as a preview, slow start, the very first, at the beginning of time, you're going to set your SS thresh to be a very high value. And the sender is going to start with a C wind of 1, and it's going to double it until we experience loss. And then it's going to set SS thresh to be half of the congestion window. The next time the sender ends up having to do slow start, and we'll get, in a few slides, we'll get into when that is. But let's just say the next time that the sender finds itself doing slow start, it's going to again start with a C wind of 1, and it's going to double its window size until it hits SS thresh. Okay. So it's going to slow start up to the SS thresh value. And once it reaches the SS thresh value, it's going to stop doing slow start, because it's going to say, if I go beyond this rate, there's a possibility that I'm going to overshoot my capacity and cause loss. So instead, I'm going to very quickly exponentially ramp up to SS thresh, and then I'm going to be more cautious about how I increase my rate. Okay? And we'll get to that in a few slides from now. So the last part of the design of how TCP works is that this question of how you adapt to the rate, how you adapt your rate to congestion, And we said that the way in which we're going to do that is AIMD. So our next question is, how does TCP implement AIMD? So let's walk through that. The first part of how you do AIMD is your additive increase. Okay, this is when you have no loss, you additively increase or you add some constant to your C wind. In TCP, this is just 1 MSS every round trip time. So in TCP, if there's no loss, the sender is going to increase its C wind by 1 MSS every round trip time. And then the other part of AIMD is the multiplicative decrease. And the way TCP does this is it says, when I detect a loss via 3 duplicate acts, then you're going to halve your congestion window. Okay, so multiplicative decrease with a factor of 2. That's what TCP does. You might be thinking, what about timeouts? When you have timeouts, what TCP is going to do is it's actually going to exit AIMD. Okay, so what TCP does on timeouts is to say, the rate I have is bad. This is not I don't actually know whether I'm anywhere close to a good rate. So it's going to do the conservative thing and restart the learning process. And so we'll do that in a few slides from now. So how does TCP implement additive increase? So we said that we want to increase C wind by 1 MSS every round trip time. The way this is going to be implemented is, over 1 round trip time, we get a large number of acknowledgements. And we only want to increase by 1 MSS over that entire window or over all of those acknowledgements. And so in order to implement this in an ACK-clocked manner, we're going to add a fraction of an MSS every time we receive an ACK. So more specifically, when a TCP sender receives an ACK, and here I'm assuming an ACK for new data, it's going to increase its C wind by 1 over C wind. Okay. The 1 over C wind is in terms of units of MSS. So if you wanted to think about this correctly in terms of bytes, you'd be increasing it as per this gray equation here that I added. I just wanted to put it here, we've been doing all our calculations in terms of MSS, units of MSS. This is the one place where I wanted to put in bytes because this is the one place where I found it's easy to get confused, right? And so why is it what this equation says? So if you take 1 over C wind and you say how many I want to do that calculation in terms of bytes. The 1 here corresponds to 1 MSS, which is why we have the first term MSS here. And then we want to increase by a fraction over the number. Every time we receive an ACK, we want to increase by 1 over MSS, right? So we want to divide this by the number of ACKs that we would expect. And the number of ACKs that you would expect is the CWIND, that's the total number of bytes sent over a round trip time, divided by the MSS, which is how many bytes you can fit in any one particular packet. That's going to be the number of ACKs you receive. And so we would have divided, to get the fraction that we have to add each time you receive an ACK, we would divide MSS by the number of ACKs, which means we would divide MSS by CWIND over MSS, which is why we get this term here where we are multiplying by MSS over CWIND. Okay, I hope that was clear. So moving on, the reason this works is because after a full window, or after we've received CWIND worth of packets, we would have increased our CWIND by exactly 1 MSS. Okay. And so if we're increasing over the course of an entire CWIND, we are increasing by 1 MSS. Remember that we send a CWIND over the period of a round trip time. So that means we've increased by 1 MSS per round trip time, which is exactly the behavior we were hoping for. Okay, so how does TCP implement multiplicative decrease? This is very straightforward. When you receive your third DUPAC, we simply cut the congestion window by 2. And then lastly, when we have a timeout, how does TCP react? The rationale here, again, as I alluded to earlier, is when do you get a timeout? You get a timeout when you've lost multiple packets in a window. And this tells the sender that the current congestion window might be quite incorrect or quite far off from where it needs to be. And there's multiple reasons this might be the case. It could be you had some other competing flows that suddenly came up. It could be that you had a routing change and your bottleneck link is no longer the same. Any number of reasons. The sender doesn't know. All it knows is that it lost a whole bunch of packets, and so it's unsure whether the current value it has for CWIND is any good. And so what TCP is going to do, or the particular design choice that TCP decided to do, was that to say, I'm going to throw this CWIND value out and I'm going to restart. So I'm going to rediscover a good rate from scratch. It didn't have to be implemented this way. This might have been overly conservative. It's just the particular way that TCP, the design decision TCP made, is erring on the side of caution. And so on timeout, what TCP is going to do is retransmit that first missing packet. This is what we always do. It's going to set SS thresh to be half of the current congestion window. Remember, because this is the congestion window that has caused pretty severe loss. So it's going to remember half of that rate as being the value of SS thresh or safe rate. It's then going to set CWIND all the way down to 1 MSS. Right? So we're starting from scratch again. And it's going to enter slow start mode. Okay. So the sender is back at a place where it has 1 MSS and it's doubling or going through slow start, doubling its CWIND every round trip time. And now this is where SS thresh comes into place, is to ask yourself, when does a sender stop doing slow start and start doing additive increase again? And that is determined by this parameter SS thresh. Okay. So when your congestion window exceeds your SS thresh value, that is when the sender is going to switch from increasing its rate as per slow start to this more gentle additive increase that we have in AIMD. And let me repeat that one more time. What is the sender going to do in this case? Right? The sender has started out with a CWIND of 1. It's going to do this very exponential increase of slow start. So it's going to double its CWIND every round trip time until it reaches SS thresh. At SS thresh, it says, I knew this was a safe rate. If I double it one more time, there's a very good chance I'm going to cause packet drops or cause congestion. And so instead, I'm going to stop doubling my congestion window. I'm going to do something much less aggressive, which is additive increase. And so that's when the sender is exiting this slow start behavior and starting to enter this AIMD behavior. So let's summarize the rules we've discussed so far. The summary of the decrease rules, or the ways in which TCP updates its parameters to decrease its rate, is that it's going to cut its congestion window in half when it receives 3 duplicate ACKs. That means any loss that's detected by receiving 3 duplicate ACKs. It's going to cut its congestion window all the way down to 1 when it is on a timeout, so 1 MSS. but there's no scenario under which it's going to drop its congestion window below 1. So the congestion window minimum is always 1 MSS. If you find yourself tempted on an exam to have a congestion window of 0.1 MSS or 0.5 MSS, don't do that. Summary of the increase rules. When you're in your slow start phase, you increase C-wind by 1 MSS every time you receive a new ACK. Net effect is you double your C-wind every round trip time. When you're in the AIMD phase, you increase by a fraction of the MSS for every ACK you receive. And so in effect, over the course of a round trip time, when you've sent a full C-wind worth of data, you would have increased your C-wind by 1 MSS per round trip time. So with that, at this point now, let's actually switch to talking about, we're not switching, so we're continuing with how TCP does congestion control, but we're going to look at it from a much more implementation, almost pseudocode centric view of how TCP does congestion control. One of the things that's nice about doing this is, your second project is going to be implementing TCP reliability and how you're actually going to implement everything we've talked about with sliding windows, dupacks, timeouts, and so on in order to implement reliability. What we're going to be talking about now is not part of the project, but this is really the lines of code in some sense that you could add to your project in order to have implemented congestion control. So if you're looking for a little coding project over the break, consider extending project to do congestion control. And as I go forward, again, we are referring to C-wind in units of MSS, and I'm going to be using red, I think and hope I've done this consistently, but I'm going to be using red to denote the changes you have to make to TCP's reliability protocol in order to implement congestion control. Okay. So with that, the implementation, the state at the sender, there are 4 basic forms of state the sender maintains to implement, not just congestion control, actually this is reliability and congestion control in some sense. The congestion window, C-wind, which we initialize to 1 MSS, SS thresh, which at the beginning of time we initialize to a very large constant. This, and then as before, things we had for reliability, a dupack counter initialized to 0, and then timers again as we had before for reliability. The events that you have to react to at the sender, there's ACKs for new data, dupacks, which are duplicate acknowledgements for old data, and timeouts. In terms of the receiver, exactly the same behavior as we've talked about so far. There is no change for congestion control. You just send acknowledgements, and specifically in TCP, cumulative acknowledgements, just like before. Let's step through this in terms of the events and how the sender has to react to them. So our first event is an acknowledgement for new data. If the sender receives an acknowledgement for new data while it is in the slow start mode of operating, then the only update it has to make is to say C-wind is equal to C-wind plus 1 MSS. Okay, so C-wind, you receive C-wind packets per RTT. So after 1 RTT, if you had no drops, your C-wind would have effectively doubled. And so this is the slow start phase of TCP congestion control. So when we get to the TCP state diagram, this is the slow start state. If the sender was not in slow start, then that means it's doing additive increase. And so then the update is C-wind is equal to C-wind plus 1 over C-wind. Right? This was, we're adding a fraction of 1 MSS on every ACK arrival. Since we receive C-wind packets per round trip time, after 1 round trip time we would have invoked this rule C-wind times, and so we would have increased the C-wind by 1. Okay. This phase, and I'm introducing a new term here, this phase we call this the congestion avoidance phase. Okay. This is what we've been calling additive increase. In terms of the TCP state diagram that we're going to get to in a few slides, this is what we call congestion avoidance. And then in addition to these 2 rules, everything else is the usual, meaning what we've talked about doing for reliability. You reset your timers, you reset your dupack counter because this is a new acknowledgement, you send new data packets if your C-wind allows it, and so on. So the next event is a timeout. This is very simple. When you get a timeout, we set SS thresh to be the current congestion window divided by 2. This is for all the reasons we discussed just now. You then set your C-wind all the way down to 1, and you retransmit packets and other stuff like always. So the third event is when you receive a duplicate ACK or DUPAC. So when you receive a DUPAC, you increment your DUPAC counter by 1. And if your DUPAC counter is equal to 3, then you enter fast retransmit. Right? Everything up to this point is exactly what we've talked about doing for reliability. The change now is you're going to set SS thresh to be equal to CWind by 2. Okay? Because again, we've detected a loss where we know this is no longer a safe rate. So we set SS thresh to half the current congestion window. In this case, we also set the congestion window to be half. Okay, so we do CWind by 2, but never less than 1. Right? So take the ceiling of those. And you retransmit the packet and so on as always. Okay. What this is doing here is we're saying we have an isolated loss. So we're going to do AIMD, and this is the multiplicative decrease phase of AIMD. Okay. So you're doing AIMD after fast retransmission. I'm going to pause here. I can't actually ask if you have any questions, but we'll have a chance to do questions in our next lecture. So where does that bring us? I want to now go back to last lecture. We talked about TCP has this sawtooth pattern. I want to go back to that and make sure that you're now following that sawtooth in the context of how TCP is actually updating all these parameters and so on. Right. So what are we showing here? We're plotting the current window size at the sender on the y-axis over time as the TCP connection proceeds on the x-axis. And so we see this initial exponential curve. This is slow start. And then we see these two events where we dropped our window size in half. This was caused by fast retransmission. How do we know it was caused by fast retransmission? Right. We know because if we'd had a timeout versus just 3 DUPACs telling us we had a loss, we would have dropped the congestion window all the way down to 1. Right? The fact that we cut it in half tells us this was an isolated loss. And then again, we have this additive increase or linear increase phase after we do a multiplicative decrease. And then now here, let's say we have a timeout. So what you should expect to see is your congestion window drops all the way to 1. Right? That is what I'm showing here. We're also going to remember SS thresh as being set to half of that congestion window. Okay. And now remember we dropped to 1, and as per the TCP rules we've discussed today, we're going to restart in slow start. No, sorry, not restart in slow start. The sender is going to once again go back to doing slow start. And it's going to do slow start until its current value of CWind crosses this value we've remembered for SS thresh, at which point it's going to switch to doing linear increase again. Okay, so this is at this point you've understood mostly we've seen most of the TCP sawtooth behavior, which goes back and forth between being this exponential growth of slow start, dropping your congestion window either by half or all the way to 1, and then ramping up doing either a linear increase or by restarting slow start. Okay. So we have one final phase in how TCP does congestion control that we need to discuss, and that's something we call fast recovery. And fast recovery is an optimization really to the congestion control logic and algorithm that we've discussed so far. And what it's trying to optimize, or the problem it's really trying to address, is this issue that arises in congestion avoidance, where when you have really a single packet drop in a fairly large window, then congestion avoidance, this process of additive increase and having cut your window by half, is really too slow to recover. It stops the sender from sending as fast as it could have. And we're going to do a detailed example to show what the problem here is. It is an optimization. It is a bit of a hack at some level, but it's also kind of cute and effective, I would say. So fun to walk through. Let me walk through an example and then come back and recap at a high level what the issue was. And this example, again, we're counting packets, not bytes. You can always just multiply by the MSS to obtain the same example, but working in terms of bytes. And in this example, we're going to consider a TCP connection in which we're going to say that the congestion window at the sender was set to be 10 packets, or had achieved a size of 10 packets. And we're going to say that the last ACK that the sender received was for packet 101. Okay, so this is the next packet it's expecting is a packet that has a sequence number of 101. And so currently the sender has 10 packets in flight. That's packets 101 to 110. And the scenario we're going to walk through is where packet 101 is dropped. And the steps we're going to reason through is asking ourselves what ACKs are going to be generated by the receiver, and when the sender receives those ACKs, how is it going to respond? And again, we're assuming the only packet or ACK that's no ACKs dropped, and the only packet that's dropped is 101. And at this point, I would encourage you to actually pause the video here and first try working through it on your own, and then move forward with me once you've had a chance to think about it on your own. Okay. But so moving forward, what I'm going to show you here in this example is the timeline of events and actions at the sender. And so recall what we have in flight are packets from 101 to 110. Those had already been transmitted by the sender when we first stepped into this example, and packet number 101 has been lost. Okay. And we're going to walk through the timeline where we're going to say what the sender does. So here's the first step. The sender is going to receive an acknowledgement that says ACK 101. Okay, it received this acknowledgement because at the receiver, packet 102 made it through. And remember, the receiver always does cumulative ACKs and says what the next expected packet is. And so the receiver sent an ACK that says ACK 101 to the sender. In parentheses here, I'm saying due to 102 so that you realize that the sender is receiving this ACK because the receiver corresponding to packet 102 when it made it through to the receiver. Okay, so at this point in time, the sender has received ACK 101, which was because of data packet 102. It had a congestion window that was set to 10, and this is a duplicate acknowledgement. So it's the first duplicate acknowledgement. So the sender is not going to transmit or do anything at this point. It's going to receive another duplicate ACK, this time due to packet 103. So it's going to increase its dupack counter. And yet another ACK 101, this time due to 104. And so it's going to increase its dupack counter again. At this point, it has 3 duplicate ACKs, and so it's going to do fast retransmit. What this means is the sender is now going to retransmit packet 101. And then if you follow the rules we had for fast retransmit and congestion avoidance and so on, at this point, the sender sets SS thresh to be half of its current congestion window value. So it's set to be 5. And then it cuts its congestion window, CWind, in half. And so CWind is also 5. And now let's look at what happens at the sender. What happens next is the sender receives another ACK 101, this time due to packet 105, but it doesn't transmit. It can't transmit. It has a CWind of 5 and it has more than that number of packets outstanding. Same thing due to 106 and 107. I just want to point out that notice we do not restart the dupack counter on the same packet. Okay, so if you're not going to do fast retransmit a second time, okay, the dupack counter does not get reset. You only retransmit when you have 3 dupacks. So if you actually lost the same packet twice, you would be falling back to a timeout to retransmit it. Okay, so we did not restart the dupack counter, so we're going to keep going. And this time the sender receives yet another ACK 101, this time due to packet 108. Same thing for 109, 110. And it's only when 101 makes it to the receiver, then the sender receives an ACK that says ACK 111. That's because 101 filled a hole at the receiver. By the time it got the retransmission, it had received everything up to 110. And so the receiver sent ACK 111 due to 101. And so at this point, the sender now has a congestion window of 5. And it has no packets in flight. And so it can actually start to transmit new packets. The main problem here is that this was a long time to wait at the sender. Right? It spent all of these dupacks coming in, which are a clear sign that the network is delivering packets to the receiver, but the sender just stalled. And you can imagine if you have a window of 1,000 packets, how much worse this could be. A somewhat secondary issue, I would say, is that in effect, we've drained the network pipe. We've drained the pipe. There are no more packets in flight. And we've lost all of that ACK clocking that we had going. And so now the sender has to rebuild that ACK clocking. So at this point in time, with a CWind of 5 and 0 outstanding packets, the sender would just dump another 5 packets straight into the network, right, in a burst. So all that we were trying so hard to avoid bursty behavior, well, we've just undone it. But this is the problem that fast recovery is trying to resolve. So 2 questions to ask yourself before you move forward. First is, do you understand the problem? Okay, the crux was that the sender had to wait a long time before it was able to resume sending. And secondarily, that once it was finally, when it could finally send, when the retransmitted packet made it through, we had lost ACK clocking, and so the sender was just dumping a full window into the network. If you haven't understood this, I would say pause here, go back to the previous example and work through it until you do understand it. And once you do, then second question is, how would you fix it? And again, I would encourage you to pause here, think about how you would fix it before proceeding and having me tell you how to fix it. Okay. So with that, the fix we do have is this technique called fast recovery. And the basic idea is, very much what you might expect, which is we're going to give the sender temporary credit for every duplicate ACK that comes in. This allows us to keep packets in flight. This allows the sender to continue to send new packets as long as these duplicate ACKs are coming in. And again, the intuition here is that if the sender is receiving duplicate ACKs, this kind of tells the sender that the network is functioning pretty well, because it's the receiver's receiving packets and sending ACKs, and the ACKs are making it through. So exactly how do we do this? The rules are as follows. Under fast recovery, when we have 3 duplicate ACKs, we're now, as before, we're going to set SS thresh to be half of the congestion window. But we're going to now give the congestion window credit for those 3 duplicate ACKs. So we're going to say that the congestion window is SS thresh, so it's cutting in half, plus 3. And then for as long as we're in fast recovery, every time we receive a duplicate ACK, we're going to increase our congestion window by 1. The intuition or the hope here, what this is trying to achieve, is that this allows the source to send an additional packet. That is kind of in the conservation principle, it's a 1:1 for the packet that arrived. So the packet that generated the dupack left the network, and so we're allowing the sender to put in a new packet. And we're going to let the sender keep doing this until it exits fast recovery. And the condition under which it exits fast recovery is when it receives a new ACK. So when it's received a new ACK, this tells the sender that this issue with this isolated loss is resolved, and it can now go back to what it originally intended, which was to get back into AIMD, but to do it with a reduced congestion window. So we set the congestion window to be SS thresh, the original half that we had saved. So let's go back to our example and see that in action, and I think it should be clear, I hope. So here's again the timeline at the sender. Same scenario, 101 was lost, the other packets make it through, but now we're going to do fast recovery. So just like before, we get ACK 101 due to 102, due to 103, due to 104. At this point, we have 3 duplicate ACKs. And so like before, we're going to retransmit 101. Also like before, we set SS thresh to be half of the congestion window, so it's 5. But now, because of fast recovery, we're going to set CWIN to be 8, which is 5, plus the 3 dupacks that we're giving it credit for. Okay, and now the subsequent steps are where things continue to be different. So the next ACK, or duplicate ACK 101, that arrives at the sender, it's going to increase its CWIN by 1. So the congestion window is now 9. Okay, that's still smaller than the number of packets in flight, so the sender is not going to transmit. Same thing when it receives yet another duplicate ACK due to 106. The CWIN is 10, but the sender, remember, already has 10 packets in flight, so it can't send more than that. But the next ACK that comes in due to 107, the congestion window is now 11. And the sender only had 10 packets in flight. So now the sender is allowed to send 1 more packet. So it sends a new packet, 111. Okay, that was the next one in order. Same thing for the next 2 pack. Your congestion window is 12. Sender gets to send 1 more packet. Again, the next one, congestion window is 13, so it sends 113, and so on. Until finally, packet 101, the retransmission of 101, makes it to the receiver. And then the receiver sends an ACK that says ACK 111. Okay, this is due to the retransmitted 101 arriving at the receiver. So at this point, this is a new acknowledgement, right? So this is no longer duplicate ACKs coming in. And so this is the point at which we exit fast recovery. And exiting fast recovery, remember, means that we now set the congestion window to be 5, which is equal to be SS thresh. Because recall, the original intent was we were going to do multiplicative decrease and drop our congestion window in half. We were just temporarily inflating the congestion window to allow the sender to keep going. But now we're going to do multiplicative decrease, so we set C wind equal to SS thresh, which is 5, and you can transmit 115. Okay, why 115? Because your C wind is 5, and we already had 4 packets, 111 to 114, that were in flight, and so we're allowed to send one more packet in order to have those 5 packets in flight. Okay. And so what would happen next, just to make sure you see where this is going to go, the next step, the sender would receive an ACK 112. Right? This is due to the packet 111 arriving at the receiver. So at this point, it would update its congestion window in accordance with the congestion avoidance rule. So it would be 5 plus 1 over 5, right? 1 over C wind, and so on. And from here on, it would continue to do the normal additive increase and so on. So this is the end of the example of fast recovery. I hope you see why we needed it in order to not stall the sender when all you had was, bad luck, one packet that got dropped, and also how it works by temporarily giving the sender credit or inflating its congestion window in proportion to the number of duplicate acknowledgements that are coming in. So let's see how that updates the rules we had, or the pseudocode we kind of had, for how congestion control works. And the changes, again, it's clever. The changes are not widespread. They're fairly surgical to what we had before. So here's the changes. On the first event where you receive an ACK with new data, if you were in, the only changes, we now have this check that says if you were in fast recovery, then you need to exit fast recovery. Because remember, we said you exit fast recovery when you finally get a new ACK, which means that that hole you were trying to plug has been filled. So if you get an ACK for new data and you were currently in fast recovery, then we set the congestion window to be equal to SS thresh. That implies we're going to leave fast recovery. The other is when you receive a duplicate ACK, the changes are again in red over here. If this is your third dupack, then just like when we had fast retransmit, we're going to set SS thresh to be half the congestion window. We're going to halve our congestion window. Now the only change is we're adding this credit plus 3 due to the 3 dupacks that were received. And then beyond that, anytime your duplicate ACK counter is above 3, that means you are currently in the fast recovery phase. And so at that point, you set C wind is equal to C wind plus 1 MSS. Okay. And this, of course, when you get a new ACK, your dupack counter will be reset. You will set your congestion window to half, as we discussed, and you'd proceed. So you automatically get out of fast recovery. So with that, one final topic that kind of brings this entire lecture together on one slide is to take a look at the TCP state machine. And again, the TCP state machine is really just capturing everything we've covered in this lecture. It's just doing it in a very different format in the style of a state machine and transitions between those states. So we have 3 states. As we've covered, these are slow start, congestion avoidance, and fast recovery. And we're going to look at what events cause the sender to transition between these states. And so the first one, just the easy one, anytime you get a timeout, right, from whatever state you're in, you fall back or you move back into the slow start phase. Okay? So no matter where you start out, you get a timeout, you end up in slow start. Now let's look a little bit at the slow start state. Right? What happens if you get a new acknowledgement and you're in slow start? You just increment your congestion window as per the new ACK rule. So you add plus 1 every time you get a new ACK, but you stay in slow start. Right? This is your exponential growth. Until, so you're updating your C wind every time you get a new ACK. If your congestion window exceeds your SS thresh, that's when you move from slow start to congestion avoidance. Right? So if you remember, this was the discussion about I've reached up to a safe rate. Beyond this point, I'm going to be more cautious and move to additive increase. So if your C wind is greater than SS thresh, you move to congestion avoidance. And then the last event that can occur in the slow start phase is that you receive a duplicate acknowledgement. So when you receive a dupack, you increment your counter, you stay in slow start until you receive 3 duplicate ACKs. If you receive 3 duplicate ACKs, you transition to fast recovery. Okay. So now we would be in the fast recovery state. Let's move on and take a closer look at the congestion avoidance state. So we said if you get a timeout, you go to slow start. If you get a new ACK and you're in congestion avoidance, you just stay in congestion avoidance. You update your congestion window accordingly and so on, but we stay in congestion avoidance. If you get a duplicate ACK, again, you stay in congestion avoidance, increasing your do-pack counter until, once again, if your do-pack counter is 3, then you transition to the fast recovery phase. When you're in the fast recovery state, as long as you're receiving do-packs, you're staying in fast recovery. This is when we're going to be inflating the sea wind. And you're going to stay in fast recovery until such a point that you receive a new ACK. And if you receive a new ACK, you move to the congestion avoidance state, as we just discussed. And of course, if you're in fast recovery and you time out, then you move to slow start. And so this is really, if you understand these states and all of the transitions that are in this figure, this is a great way of checking that you've correctly understood what's going on in TCP. This state machine, together with the rules for how you update sea wind within each of these states, that really tells you everything you need to know about TCP congestion control. Yeah. One last point to make is, I mentioned this last time, there are many variants to TCP congestion control, and we've discussed one particular implementation. Just to give you an example, TCP Tahoe, for example, is a variant on TCP that's a very old one, where even when you got 3 duplicate ACKs, it would set the congestion window to 1. So highly conservative. It would just fall back to slow start every time you got a loss. TCP Reno does pretty much what we described today. It has a congestion window of 1 on timeout and cuts its congestion window in half on 3 do-packs, just like we do. TCP New Reno does everything TCP Reno did, but it adds fast recovery, right, which we just discussed. A slightly different variant is TCP selective acknowledgements. This incorporates a different type of acknowledgement in which you now carry these selective acknowledgements that enumerate the byte ranges that the receiver has received. And this would be carried as a special option field in the TCP header. And so selective acknowledgements are nice because it takes away a lot of the ambiguity that we saw with cumulative acknowledgements. However, it does require this new type of acknowledgement field, and it does require options in the TCP header. And so the implementation is a bit more detailed and a bit more involved. You might be wondering what's with the Tahoe Reno, New Reno. It's that the Berkeley Unix group used to have these retreats in Tahoe, and they would name what ideas they came up with or the changes that came out of those retreats based on the location where they'd had their meetings. Fun fact is that many of the research groups at Berkeley in the systems side continue to have these annual retreats at Tahoe. So that tradition is continuing till today. Anyway, in this class, unless we tell you otherwise, you can assume that we are basically describing, if we say TCP congestion control, we are assuming everything that I've described in today's lecture. This is effectively TCP New Reno. And that's going to be our default assumption. One question you might have about all of these variants is interoperability. Right? If everyone's running a different variant, how can all these algorithms coexist? Right? Don't we need a single uniform standard that we all agree on for how you implement and update your congestion window? So specifically, what happens if I'm using TCP Reno and you are using TCP Tahoe? And there's a question of fairness that we'll get to in the next lecture, but for now the question was just basic interoperability. Will the connection even work? Can we communicate if we're running 2 different variants of TCP? If you think about it for a second, you'd see that the answer is yes, because the only thing that these variants are changing, like Reno versus Tahoe, is the rules by which the sender is updating its sea wind and the number of packets it's putting in. But we're not requiring or demanding any kind of different behavior on the receiver. The receiver is just sending cumulative ACKs like it always did. So the receiver side of the connection is oblivious to what the sender side is doing to update its congestion window. And so it all just works. That is true for all of these TCP Reno, TCP Tahoe, New Reno, and so on that are just changing the update rules but not changing how acknowledgements work. If I asked you the same question about I'm running TCP New Reno and you are running TCP SAC, can we actually exchange packets or do we have interoperability? The answer would be no. And that's because with selective acknowledgements, we're actually changing the acknowledgement field. And so we need both ends of the connection to agree and understand what that change is. Right? We need the receiver has to be able to send selective acknowledgements, and the sender has to know how to update its sea wind based on those selective acknowledgements. It has to know how to parse them, what the semantics are, what the logic around updating sea wind is. Okay, so we do have interoperability, but only between variants that don't actually change what goes into the TCP header or the acknowledgements and that get carried between them. And so with that, at this point, I hope you have a pretty detailed understanding of how both congestion control and reliability are implemented in TCP. And topic for next lecture will be getting into some of the more advanced congestion control techniques, including a little bit of router-assisted congestion control, as well as a little bit of kind of trying to derive the simple analytical model for the performance we can expect from TCP. With that, thank you, and I hope to see you next week in class. So